Okay, so 11.4 is called conditional probability, and it kind of actually is the way it sounds. The easiest way to calculate conditional probability is using a two-way frequency table, and so this will typically be filled out for you, and then you just have to know what you're looking for and how to find it. So conditional probability happens in real life all the time. It might say, what are the chances it's going to rain given that it's May? You know what I mean? But read that for some more information. So, conditional probability, this is the formula. The symbol, it's a up bar, but that means given. So you're going to read it as the probability of event A happening given that B has already happened. So it's kind of like a double probability. It's a subset, okay? Because you already have to have part of the population occur, and then you're taking the chances out of that. So it's not going to be out of the entire total, if that makes any sense. Now, mathematically, if you like formulas, then this is going to be for you. On top, since B has already happened and you want A to also happen, it's going to be the intersection of when they happen at the same time. At the same time. And so there's going to be two different categories that they're talking about. So maybe it's eating chocolate and being a boy. And so on top you would say, well, how many ways can I eat chocolate and be a boy? So in a table you would look for where the two columns intersect, column and row intersect. Does that make sense? And your new total is the part that already had to happen in the first place. And so I always call this, it's the given part. All right. And so like if it was given I was a boy, like what is the probability that I will eat chocolate given that I'm a boy? Well, on top, I would have the probability of chocolate and a boy. And then on bottom, it would be just boy. So it's not out of all people, it's out of the given portion. Okay, that really is the key. The top part is always usually correct because students get that idea, but it's that denominator that's missed the most. But once you remember like, oh, it's not that, it's the given is my new total. Okay, so it's like your subtotal. That's conditional probability. That really is it. So I've got two pretty simple examples, but I've done this before, and these were, I'd say, missed by about 50% of the students. So we've got these favorite ice cream toppings, hot fudge, sprinkles, M&Ms, other toppings, and then we talk about men and women. So on the two-way categories, you're always going to have two different categories. And sometimes they're related, sometimes they're not. You don't even really care. So it says, if a person is randomly selected from those surveyed, and it's always going to say that, what is the probability of choosing someone whose favorite topping is rainbow sprinkles, given that the person is a woman? So in notation, because you might see that too, it'll say choosing sprinkles, given that the person is a woman. And so that's what you would write it as notation if you want it, okay? So what you're looking at is, well, how many ways are there for sprinkles and a woman out of the probability of the given part, which is just the woman? And so since these are probabilities, we don't need to have a fraction on top and a fraction on bottom. We're just going to worry about the values, and that will create the fraction. Does that make sense? So I'm going to get rid of these. So sprinkles and women. So I look at, well, these are all the sprinkles. And then these are all the women, because, well, the women can like each of those categories. And so you want to look at where do they both intersect? When do they happen at the same time? And so we see, oh, well, there's 19 people that like sprinkles and that are women. And so on top, we would have 19. Out of a woman. So I need out of all the women though. So I'm going to look over here, and if this wasn't totaled, I would just add up all the women myself, no matter what topping they like. So we're looking at 47. And so the chances are 19 out of 47. So does that make sense? Because we want to know the probability of picking someone that likes sprinkles, given that they're already a woman. So I'm not looking at the men at all. I'm now looking at kind of like, this is my new total, and I just want to know how many of those like sprinkles. That's the whole concept. All right, let's look about lunch. So we could talk about pizza, hamburger, other, boys and girls. So estimate the probability that a randomly select person will be a boy given that they ate a hamburger for lunch. So on top, we want a boy and a hamburger. How many boys like hamburgers? Out of, well, I'm only selecting out of the people that ate hamburgers. That's my total. So we look at boys and hamburgers, and we see there are 14 boys that ate a hamburger out of all the people who ate hamburgers. So all the people that ate hamburgers is 16. So 14 out of 16, which reduces to be 7/8. Please try to show me that non-reduced fraction, just in case there's an error reducing, because that happens too. But that's it. So find the probability that we'll pick a boy given that they ate a hamburger. So that's why we're only picking out of all the people who ate hamburgers. We just want to know the boys. All right, now what we can do is we can kind of compare and actually see like which one is more likely or which one is less likely. And so that's really about kind of as hard as it can get. It's just a comparison. So on a quiz, I would want to see your justifications, and justifying is really just your two comparisons. So we're talking about jogging and siblings. So using the data, determine whether a student with two older siblings is more likely to jog if one sibling jogs or if both siblings jogs. So first we want to kind of write this in our notation. So we're going to do the probability of jogging. Sorry, I was going to write jogging, given you have one sibling. And we're going to compare it to the probability to jog or if both siblings jog, given two siblings jog. Okay, so how many, if we jog, we've got given one sibling jogs. So I get 416 out of one sibling jog. So I need to add those together. Do a little bit of math. So 416 divided by parenthesis 1823 plus 416. I got 0.1858. I'm just going to stop there. So about 18.5%. Compared to the probability that I will jog given both siblings jog. I know I wrote two siblings, but that should make sense. So they intersect at 400 all over my total, 1380 plus 400. So I'll go ahead and do that. I know I didn't bring my calculator, it's just faster if I don't. So 0.2247. So it is definitely more likely if both siblings jog. Okay, so just comparing. All right, independent and dependent events using a formula. So we kind of talked about it thinking, and this is the formal formula. So two events, A and B, are independent if when we do their intersection, it's the same as when we multiply their individual probabilities. Okay, so let's do an example of that. So here's our two-way table. So determine whether or not the event's female and was a teenager at first marriage if they're independent. So we're going to look at the probability of female and teenager and compare it to probability of female times probability of teenager. Okay? If they're equal, it means it's independent. If they're not equal, then it means they are dependent on each other. One did affect the other. So the probability of female and teenager. So here's female, and what is E? I think I cut off the table. E, W, and H.